What are the learning objectives for today? First, I will go through key concept of simulation for fusion that will help you to use the software more proactively because you would understand the key driving ideas behind the software. Then I will talk about the linear static stress, the most commonly used simulation, and do an example of how you validate this jack and find out if it would transfer the load that is needed. I will talk about Modal and about how to avoid critical frequencies and do example of that. With the thermal, I will describe how to use it and show you how to fix a problem with the overheating. And for thermal stress, I will show how we can optimize the design and make it smaller, but still perform as we want. And at the end of the class, I will do a preview of the cloud simulation technology. So let's start with the key concepts, with the key driving ideas behind the software. What is simulation for fusion? Our mission is to simulate behavior of design in various scenarios. In other words, we are alternative to experimental testing. And that's a core idea of digital prototyping. Instead of wasting your time and money by doing multiple physical prototypes, you can very quickly iterate and find the optimal solution using the digital prototype. But simulation for fusion is not only about finding if the design would work or would break. It's also going to give you the directional guidance how to improve it. So the software leads you to the good design decisions. And of course, we are part of Fusion 360 Rich Data Collaboration Experience. So there are a couple of key concepts: loads, constraints, contacts, studies, and results. And these clicks together to simple simulation. So let's start with loads. Loads define forces, moments, and so on applied to your design. Loads are actually causing stresses and deformation of your design. And we have multiple types of loads. We have there force, pressure, moment, that's the torque applied to your design. Remote force, this is the force that is acting outside of your design. And for thermal, we have applied temperature that describes the temperature of a given surface. Surface heat that describes the heat that is generated by the square units of the surface. Radiation, convection, that's a common cooling mechanism of transferring the heat between the surface and the liquid or gas. And internal heat, this is the energy generated inside of your body. Let's make a quick example of that. So here, I'm going to apply quickly a load. So I'm clicking to the icon for structural load, selecting the surface, putting there the magnitude, let's say 1000 newtons, and clicking OK. So quickly, I did the force here. There is a very self-explanatory icon, and in the browser, you see the representation of it. You can make it more complex, so let's go and edit this force. I'm going to double-click it and show you a couple of more things you can do with it. First is that you can select multiple targets, so multiple surfaces that the force acts on. Or vice versa, you can limit the force to just the part of the surface. So if I will limit target, I can use this little manipulator and eliminate the force just to this part of the surface. And I can also move that to better describe the problem. There are a couple of other options how to specify the direction. Perpendicular to the software, using angle. In this case, you can use these manipulators and change the direction using the angular input. And vectors will help you to define XYZ coordinates for the force. And the last one is the reference angle, when you can select any entity and the force is going to be aligned with the selected entity. And similar, there are a couple options for the thermal load. So for thermal load, I'm going to work with a convention in this quick example. And you want to make a convention using all these surfaces there. And there is multiple surfaces, so it will take a time to select it. So there is a very useful option to select all faces, and you just click there. It selects all faces, and then you can just unselect the faces that should not be part of it. Next concept is concept of constraints. So constraints limit displacement of your design. Constraints describe connection of your design to the rest of the world. That means that you need to make a decision what you are simulating and what you are not simulating. So for example, if I'm doing a simulation of this computer, of the lid of it, I can just model the lid and then put a pinned constraint to the bottom of it. Or I can say I need to simulate more, so I will make a model of the whole computer and put a constraint to the bottom of the computer. Or I actually may want to also calculate the deflection of the desk, so in that case I will need to do a model of the desk and put a constraint to the bottom of these legs. Or maybe the vibration of the floor is important for me as well, so in this case I will need to model the floor as well and put constraints around it. Well, but you will need to make a decision when you want to stop and eliminate what you are calculating and what not, and that's what constraints are for, to define the connection between your design and the rest of the world. And by the way, it's a good practice to make that as small as possible. So in my case, I probably don't want to calculate the vibration of the floor as a part of the analysis of the lid of the computer. We have multiple types of constraints. Fixed one, that's like welded or glued. Pinned allows rotation. Frictionless, that's about slipping two surfaces. And prescribed displacement is very similar to fixed, but it also says what will be the deformation. So there is a force deformation in the fixed constraint area. It's pretty easy to set up a constraint. You click to the constraint icon, and then you select one surface, or actually multiple surfaces, to put at the constraint. You see the icon for constraint, and you can have it fully fixed, or you can actually remove the degrees of freedom in some axes, and then the icon changes as well. It's similar for a pinned type of constraint, where you have the ability to have it free for tangential, it means rotation, movement along the axis, and radial.
Did you do this on OBJ or Mesh basically before, or was it specifically on Modal?
Well, you can import whatever design you want into the Fusion through the step or other neutral formats, or we have a good connection to Inventor that's smarter and help you to bring even some features inside.
I think the key is you need a good solid model. Yeah. If you're doing a mesh model, you can as long as it's a solid model. So if you go using some of the techniques Alex showed us yesterday, if you go towards the solid, then you can.
Okay, next is concept of contacts. Contacts define connection between components. So if you have multiple components, you need to define how they interact with each other. And we have multiple types of contacts. The bonded contact, you can imagine it as glued or welded together. Separation without sliding allows the surfaces separate but without any sliding. Sliding, no separation, means that there is a free sliding, but the surfaces need to stay touching each other. And the last one, separation with sliding, that's a combination of it. So it can slide, it can separate, but the materials can't penetrate each other. And because there are a lot of contacts in your design, there is an automatic contact generation that help you to do that very quickly. And we also have a degree of freedom analysis tool that help you to identify missing contacts and constraints. So let's take a look how it works. I have this simple assembly with multiple components. I need to put contacts between them to be able to solve it. There is a nice view called Groups View that helps you to identify missing contacts. So now I switch it on and it's all gray. It means no bonded contacts. And I can start adding that. So I will click to the bonded, and the software offers me to do the contacts automatically. But I don't want to do it right now. I want to show you how to do it manually. So I'm saying no. And now I'm selecting two bodies I want to contact together. So I'm selecting this one and that one. As soon as I do it, it isolates the view nicely. So now you can go and select the first surface, and it highlights the second body, and you should select the second surface. As soon as I did it, you can see that now it has a blue color, but the rest is still in gray, so there are still missing contacts. Well, now I will use the automatic contact generation, and you can see that almost anything was bonded together, but this one is still not. So let's take a look what happened. And you can see there is a clearance here, so the bodies are not touching each other. So I can do manual contacts, or I can actually take advantage of settings here, and there is a contact tolerance that tells you when these things will be bonded and when not. So I'm going to increase the tolerance, let's say to 2, and run the automatic contacts again. And now you can see everything is blue, so everything is connected together. Contacts are presented here in browser, so you can see for the last two, you can see the two colors that are indicating where the contact exactly is. And you can see that these are bonded contacts. However, this is not a good place for bonded contact because it can rotate, so I can adjust it. I can select these two and click to edit contacts and change bonded to sliding. And I'm done with contacts. Not yet. I mean, that's the idea we are talking about for a long time, but we didn't unify the joints in the assembly and joints in the simulation because there is very similar stuff, but there are also differences. So this is still in front of us. So next is concept of studies. Study contains definition of simulation and results, and studies actually allows you to do multiple analysis on one design. So let's say you can do the static stress and modal on one model, or you can do multiple load cases. So for example, you can put multiple type of loads and moments or different magnitudes, and all of that can be managed by multiple studies. Well, by the way, this shows how dynamically we are developing the software. In summer release, we introduced the static stress and modal frequencies. And then in the autumn release, there was a volume mesh. And now in the winter release, you will get the thermal and thermal stress that I'm going to demonstrate as well. So this is the newest addition to the Fusion family of features and pretty quickly growing. So you can expect a lot from simulation team. And the last concept is concept of results. So results allow you to explore calculated stress, strain, deformation, and make decisions about your design. In results, you will find answers to your questions like what is the stress in my design? What is the deformation of my design? Would it break? Where can I remove material to optimize my design? So you are finding your answers here in the results. And the basic idea is that the model is covered by colors. And colors means numbers, and there is the legend that maps the numbers to colors. That's how we communicate the idea about stresses being inside and on the surface of your body. So let's quickly take a look at it. Now I'm in the results, and I can see the legend here. So for example, I can see that blue means safety factor 15 or more. I can use legend to actually take a look inside to my model and eliminate some parts of it from the display perspective. So, for example, I can do a thresholding and show you just pieces of the design that are loaded a lot. So these are the pieces where there may be a problem in the design, or the design at least is well used, so the material is really transferring the stress. Or I can do from the other end and show you the parts of your design that are actually over-designed because the safety factor is really high, so you can maybe remove the material in these parts of your design. Or you can actually show both. So you can show the combined view of the pieces that needs your attention because of under-design it and because of over-design it. So these are like the areas of interest of your model. Well, the legend also lets you to switch between different type of results. It's kind of an interactive control to take a look what was calculated. So you can switch to stresses. There are multiple type of stresses, displacements and strain. So these things now clicks together to very simple simulation step by step. So you start with creating a simulation, then you create a study, you may review the materials, you set up your constraint, you put there a load, and then you will see the results. So this is very basic workflow from beginning to end to do the simulation. And I can quickly show it. So it's really easy of use. You click to the simulation and create a simulation. You create a study. And you can see that the icons are aligned, so you go step by step in the toolbar. So now you click to the materials. You make sure that the materials are right. You put a constraint. Next is load, let's say 3000 newtons. And you click to solve. And in a moment, you have your results calculated. So this is really easy to use tool. Every engineer or designer can use it to make a decision about the design and make the design better. Now let's talk about linear static stress. This is very commonly used simulation, so let's take a look what it can do for you. Linear static stress calculate displacement, stresses, strains, and reaction forces caused by applied loads. There are a few assumptions, like small deformations, both deflection and rotations, and linear material behavior. It is actually most commonly used simulation. Our data shows that about 80% of users are using the linear static stress. Even like the very specialized users, the simulation analysts paying a lot of money for big and expensive packages, they are still using the linear static stress. So it is very useful type of simulation. And I'm going to do a quick example. I'm taking this jack. The function of this is to elevate a car. If you want to change your wheel, you are using this one to elevate it. So you are using the handle to move this screw. Here is the car, here's the surface, and it just elevates it. And my goal is to verify that it would work. I know that it should elevate about 600 kilograms, that's 6,000 newtons. And I know that the safety factor should be above 2. So let's do the verification. As a first step, I'm going to create a simulation and create a static stress study. Well, now let's take a look to the design. There is a handle and U-screw and an aligner. These parts I probably don't need to simulate. I can replace that by a constraint. So I'm going to suppress that from the simulation because they are not part of the problem I'm solving. And now I have here the upper arm that actually transfers the force to the main body, and there is a screw that holds that together, where the bottom part is actually touching the ground and transferring the force there. So let's start with the definition of the simulation. I'm going to put a load there, and it's going to be 6,000 newtons for 600 kilograms. And here I remove the aligner, so instead of that I will put there the frictionless constraint that kind of represents the car that is touching here but can slip. And it's holded to the ground by this surface, so I would put the fixed constraint there. Okay, so I think I'm done for simulation with the definition. However, I see the yellow color here indicating that there is something that needs my attention. So I will click to the pre-check, and it's going to tell me that actually the contacts are missing because I forgot to do the contacts. So let's select the degrees of freedom view to show how it looks. And now you can see that the green color says it's fully constrained, fully fixed, because there is a fixed constraint between the ground and this part. And this one is potentially fixed because there are some constraints, but not enough. And the rest is in the red color. That means that it's not fixed because I didn't make any contacts there. So let's do that. And instead of doing the contacts manually, I'm going to ask for automatic contact generation. And now if I display it, everything is green, everything is constrained. So I'm ready for simulation. I'm going to click to solve. And now it generates quickly the mesh and solves the equations to give me the results. You can see it's pretty fast. I have a small, not much powerful computer, but the calculation really takes just seconds there. And here are the results. So the legend shows me that actually the minimal safety factor is 2 point something, so it's above 2. So I verified that this jack will do its function. It will elevate the car and it will not break. But I can actually take a look and learn more about my design from these results. So let's display Statis. And I can, for example, take a look what parts of my design are loaded a lot. So I will do some thresholding. And now you can see that this screw is actually loaded a lot. And it kind of makes sense because take a look how big this body is and how big the upper arm is. And the screw is also taking the part of the power, but it's really small. So probably I have a little over-designed these two pieces relative to the size of the screw. And then you can see that also around these pins there is some stress accumulated. So probably there is a space to make the design better, maybe change the dimensions there. And also in the part where the car is actually touching the jack, it looks there are some stresses. So I'm good. It's over the 2 safety factor, but still I can do improvements there. Or I can display it from the opposite perspective and actually display parts of the design that are not loaded much. So let me do the thresholding in the opposite way. And now you can see that actually this bottom part is almost not loaded. So the load there is really small. It's actually about 26 megapascals only. So it means that I probably can do a lot of optimizations there. And it's also kind of self-explanatory. If the force is going down through this pin and it freely rotates around this pin, this one doesn't carry much load. It's there to position it under the car and to better fit the space. However, it doesn't transfer any load, so it could be much tinier. So this is a type of the directional guidance that the software gives me to do a better design decisions. And there's one additional thing that would help you to better understand function of your design, and that's animation. So I'm going to adjust the deformation by factor 2. So now you can see that, well, this deformation that's in reality a fraction of a millimeter is shown in a big way, so you can understand the deformation. And now I will start the animation. And the animation shows you how the design behaves when loaded. So you can see that as the force is coming here, it deformates. There is a deformation here, and you can also see colors changing. That means the stress is generated inside of your design. You can actually combine the thresholding with the animation. So if I would do a little of thresholding here, you can see it starts with a 0, so it's transparent, and then the stress is generated. And if you will take a look here, the stress will never go to this area, so this is really not loaded much, and you can do optimization here. Or I can do a thresholding really only in the upper part of the design, and then you will just see the pieces of the design that are really loaded. So it will kind of highlight you how the stress is coming through the areas of the design that may need some of your attention. So the easiest way is to switch here to the displacement, and it will tell you the values. So you can see that the biggest one, the red one, is actually 0.9 millimeters here. Well, if I will go to the actual, well, the deformation is so small that the naked eye is not able to see it. So you are not able to analyze it. That's why we have these, you can perceive it as a magnification tool that will really make it so big so you can understand that it deforms. It's like if you will zoom it. So it's better to understand your design. It's good to zoom in because you will clearly see what's happening.
So that's like an exaggeration.
Yep.
I would say it's not only the scale shows you by how much it's moved, but if you actually scale it, it shows you also how. Because it could be 1 millimeter, but it could be in direction and direction. So you get better understanding when you zoom and when you get scale.
Right.
Was a bit vague though.
But if I show it actual scale, so what's going on? So it's kind of hard, when I tell people, so what's actually
Yeah. I think what your boss will be really interested is this number, the safety factor. Because typically they tell you, it needs to be above 2. If it's above 2, that's safe. So if you say, I prove that it's 2.4, so you are good, you are covered because your design is safe. This is just like internal behavior of your design that gives you the directional guidance to improve because the design is never perfect. You can always do improvements there. Maybe drill some holes or weld some pieces here and there to be better and have the stress more evenly distributed through your design.
This particular jack, for instance, widowmaker, they tend to overturn. Could you demonstrate adding a side force so it can be aligned with the body of the car?
Sure, let's do that. So I would put another load and let's say put it here to this surface, and let's say it will be like 50 kilograms, so 500 meters, and 500 newtons. Let's find out what happens.
You have to change your fixed plate at the bottom, because your foot is currently anchored to the concrete base, and that's not the reality.
Right. I would need probably put something here as well, as there is a friction between the car and the. But now, without that, you can see that it turned it to this way. So let's use animation again to show that. I will make the fast animation there. Yeah, and you can see that now it's actually moving in the 2 directions. But that's based on the idea that there is a frictionless constraint here. So it can move, but in reality it would not move because the friction between the jack and car is too big. It would not allow you to move. So probably I would need to add another constraint here to limit the placement because there is not a free movement. And as soon as I do it, actually the friction between the surface and this area and friction here would probably eliminate the possibility of the jack fall out because it will be kind of, the forces will create so much friction it will not allow to slip.
But that's rarely the case, right? You get the point.
Right. I would need to simulate. Right.
Yeah, in this case, oftentimes the body of the jack moving toward the heart. The constraint of one wheel at the back, you're in the front most, so you've got this part
Right, right. In this case, I will probably need to add a simple model of the car frame or something and limit this one, and then it will emulate the whole system actually turning, because
So I think actually, right, so this, what we're doing here is just a linear analysis, right? So it's that one point in time, once it's been jacked up, right? So if you look at something like Inventor, which has dynamic simulation, you can actually look at the process of jacking it up and then do a FEA study at the end to look at what kinds of loads were generated due to the motion as well as the weight of the car. And I think that would give you a more realistic picture of that entire process rather than just this one snapshot in time.
thank you. So let's move to the next one, and that's Modal. Modal is really interesting one because it's easy to set up, but gives you interesting results. So Modal analysis finds natural frequencies for your design, and these are frequencies that should be avoided because it can cause breakage and damage of your design. And I have an interesting example here, the wine glass. And maybe you have seen in the movies the scene where somebody is holding the glass and singing, and the glass breaks. So let's calculate if it is possible and what will be the frequency and what are the shapes of that. So the modal analysis is really easy to set up. You just put there a couple of constraints and you take a look to results. And again, animation is a really useful tool here to see the results. So I'm going to run animation, and you can see what's the shape for the first mode, while the next frequency is going to make a deformation in the different direction. And we can review all the frequencies, that all of them is causing slightly different type of deformation. So mode 5 is really interesting shape of deformation. Mode 6 seems like a rotation. Mode 7 is, again, interesting deformation, and mode 8 is kind of a movement. But these are more the theoretical one. The first frequency is the most critical because it requires the lowest energy to do the breakage. So we found out the frequency that would break it. Well, this is without units because the vibration, you can't say what will be the real deformation. It will just break. So depends on the energy, it will vibrate more and more and more and break. So there's actually no real units on it. It's just showing you the shape to understand how it vibrates. And let's find out, just for this case, for the fun, how it is in reality. So if you take a speaker here, put a wine glass and microphone and start changing the frequency, it actually will break in about the same frequency we calculated. So the calculation is giving you the same results as the real measurement. And if you take a look to shapes, you can see that the measured shape and the real calculated shapes are also the same. There's just difference between the magnitude because it just calculates the shape, not the real magnitude. But you can see that both the calculated frequency and the shapes that were measured and calculated are the same. So that's kind of a nice example of how the digital prototype can replace the physical one, because doing all these measurements takes a time. It costs you some money, at least the cost of the glass. So it's nice to be able to do it digitally instead of wasting your time and energy to really break the glass. Next is thermal stress. So for thermal stress, I'm going to show you how to fix the problem of overheating. Thermal analyze temperature distribution in your design caused by heat input and output. And the assumption is stabilized heat flux. So it's a system that's in the balance. And I have here a simple example. I have a passive CPU cooler, and I know that there is a 39 watts generated by the CPU, and the maximum allowed temperature in my case is 50 degrees of Celsius. And I'm getting the report from the field that it's actually overheating. It's going slightly over 50 degrees of Celsius. and I'm going to show you how to fix the problem, how to adjust the design to go under the 50 degrees Celsius. That's my goal. So I'm going to create a simulation and create a thermal study. And now let's take a look what I have here. I have the circuit board, the CPU, and the cooler. Very, very simple assembly. So I will start with definition of my simulation. First, I will do the internal heat because I know the power of my CPU. So I can select the CPU and identify that it's 39 watts. And now I'm going to start with cooling. I will use convention and select all the surfaces here for the board. And I know from tables that there is actually 30 watts per square meter and Celsius cooling convection factor. And the temperature inside my case is about 30 degrees of Celsius. So I identified the cooling of the board. And now I'm going to hide these two to define my cooler. So I'm going to repeat the convection, select all surfaces again. But now actually this bottom surface needs to be excluded because it's glued to the CPU. So I'm going to remove it and keep just other surfaces being cooled by air. And I'm going with the same 30 watts per square meter in 30 degrees of Celsius. So that was pretty simple definition of simulation. And now let's find out how would the design perform. So I'm clicking to solve, and it's preparing the model. And even for such a complex model like this one, the machine can solve is pretty reasonable. So it takes just a couple of seconds to do that. It's pretty, well optimized solver for the linear statics test type of tasks. And here are the results. And you can see that actually there is really a problem. It's 52.96, almost 53 degrees of Celsius instead of 50. That's my goal. So I'm going to fix it. There are multiple ways how to do it, but I'm going to select the easiest one, and that's changing the dimensions here. So let's go back to the model.
The heat transfer values you put in are for flat plate heat transfer, like the overall heat transfer values, because the geometry is being taken into account.
These were kind of taken from the tables just for this demonstration. So it could be more complex to find out for various type of materials and geometries. There are some empirical rules how to select it, but for that case I just selected this one just to demonstrate it.
So as we use this, how do we figure out, because picking the right U value is key to getting the heat transfer calculation.
Well,
Or how do you figure out which U values to use when the FEA is taking GHG into account?
what I did for this demo, I just searched internet and specified the type of the problem and find the empirical value that people are typically using in these scenarios. So it looks like these factors are relative to the situation you are in. So the easiest way is to find out, like Google it. Well, if you are not into it, as I'm not, I guess if you are expert in doing thermal, you will have your own tables, or your company will have some standard procedures, what factors you should use. But if you don't, well, the Google will give you a good suggestions. So I'm going to change that just a little from 13 to 15 millimeters. And you can see that now this is going to be slightly higher. And I'm going back to the simulation. and I'm going to solve this bigger modal. And you can see that I fixed the problem. Now there is a maximum temperature lower than 50 degrees of Celsius. And now you can again do some analysis. So in my case, let's take a look how the heat is transferred. So it starts with the CPU, and you can see how it is transferred through the cooler. And then you can see that the board, because it's from ABS plastic, it's material that isolates. It doesn't take any part of the cooling. Well, there's one interesting thing. If you will go back, you can see that actually this shape is kind of rounded. So it probably would make sense to not do the cooler that's kind of a cube type of cooler, but do it more rounded, because it will be much more aligned with the way how the heat is transferred. And now it's like the designer's decision. Would I make the cooler that would be more expensive to produce, because producing this one is really cheap. You take a block of aluminum and just do these cuts in it. Or would you invest to something more expensive and do the cooler that will be shaped? It will perform better, but the production cost will be higher. So these are the guidance that the software gives you, and now it's up to you to decide if you will take advantage of it and adjust your design based on these guidances. Now let's talk about the thermal stress. Thermal stress is actually a combination of the thermal and linear static stress. So it's a two-step simulation. It starts with calculating the thermal stress. And heat causes deformation, and deformation causes stresses. So the press stresses are calculated, and then the stresses from linear static stress are calculated as well and combined together. So that's like the most complex analysis we have right now, when you combine both the stresses from heat and from the static loads. And in my example, I'm going to optimize the simple brake system here and find out what I can do to make it cheaper and smaller. So here's my design. Let's create a simulation and thermal stress study. And if you take a look to the design, you can see the rotor. The rotor is connected to the wheel, and it transfers the torque from the wheel. Then I have two brake pads. These brake pads are there touching the rotor and actually creating the friction that is slowing down the wheel. So the temperature is created here because of the friction, and there are also forces that are acting. There are 5,000 newtons force to each of these brake pads because of the braking system, and because the friction is also causing a torque. There is a tangential force, 3,000 newtons per each brake pad. That's like the removing the energy from the rotating wheel. And we know that actually the temperature here is 220 degrees of Celsius. That's like what we know about. And we would like to have the safety factor bigger than 3, but not much bigger. So that's my design, and that's the goal. And here the caliper is actually holding these two brake pads. It's doing two things: holding the brake pads and also transferring the heat out. Well, because I know the temperature here, I can very much simplify the simulation by removing the rotor, because the temperature is known, so I don't need to calculate the rotor, and I can focus on the caliper with the two brake pads. So let's start the definition of the simulation. I'm going to hide the caliper to see just the brake pads and define the simulation there. So I will start with the structure load. I know that here there is the load, and it has actually two fractions. The one that is causing the friction, and the second one, that's the tangential. And I have here the direction type for vectors that's really perfect fit for this sample. So on the x, I know it was 5,000 newtons, and on the z-axis, it was 3,000 newtons. So if I click OK, you can see now the force is actually having a direction that's combination of its z and x fractions. And I'm going to repeat the same thing on the second surface. Go to the vectors and specify again 5,000 and 3,000. So these are forces, and now we know the temperature is 220 degrees of Celsius. So let's add a thermal load there, and I will ask for the applied temperature because I know the value of the temperature, and I will select the two surfaces here and specify 220 degrees of Celsius. So I'm done with the definition of what's happening on my brake pads. So let's display the caliper and hide the brake pads, and let's constrain the caliper. These are the two screws that are holding the caliper to the rest of the car. So I'm going to add a fixed constraint there to both of these screws. And the caliper is also cooling the system. So I'm going to put there a load that's actually the convention, and I'm going to select all the surfaces here. But now I need to remove some because actually here are the brake pads connected, and also the internal part of the design is not helping much with the cooling. So I'm going to remove these internal surfaces, and I know that the external temperature is actually 20 degrees of Celsius, the common temperature, and for convection value I know here the table value 0.4, it's per square millimeter in this case. So this is a definition of the simulation. So the solve is again showing the yellow color. So I will go with the pre-check, and I didn't specify any contacts. So let's go with the automatic contact generation. I will just confirm what the software suggests me to do. And now I have fully defined simulation. So I can solve it and find out what's happening. They are just hidden, but they are calculated. If I will display it now, you can see that it was calculated inside. I just.
So if you look at the light bulb and the checkbox, the light bulb is just controlling visibility, but the checkbox is actually
And now you can see that the mesh is really coarse, so it didn't look good. It looks like the precision of the calculation wasn't nice with such a coarse mesh. So I can show you the settings here where you can change that. You go to the mesh, and then this first value is the average size of the element. So as you know, the FEA is based on the idea that you split your body to multiple small pieces, and for each piece you define the equation, how it relates with the rest of the design. So now it's about 10% of the size of the element. So I'm going to make it smaller, just 5%. And also to solve the problem with these rounded things, I'm going to ask to create curved meshed elements. So let's confirm it and call solve again. So it's going to mesh it again based on my changed requirements. And now it looks much better. This is really circular now, and the mesh is not that coarse. And the result is that actually the safety factor, the minimal safety factor is 4. And my goal was go to 3 or slightly above 3. So it's over-designed from that perspective. So let's take a look what we can do with that. There are multiple things. I may do it from a cheaper material. I can change the shapes, or I can just parametrically make it smaller. So let's display from this perspective and go back to the model. And I'm going to modify it. And here there is a degree, 40 degrees Celsius. This is this angle. So I'm going to make it smaller to save some material, and I'm going to put there 30 degrees of Celsius. I'm sorry, 30 angular degrees. And you can see that the design is now much smaller. So let's go back to the simulation and solve it again. By the way, there is the icon that tells me that it needs to be solved. So even if I forget that I did some changes, the software will notify me that the results are not up to date. And as a result, you can see we improved the safety factor. It's closer to 3. That was my goal. So let's take a look how the design performs. I can first take a look how the temperature is distributed. So let's display temperature and find out how it goes through it. So it's generated by friction here, and then it's transferred through the brake pads, and then the caliper is going to take the energy and distribute it out and cool it. And you can see how it's going out. So there is some interesting situation happening here. You can see that cooling here is not optimal because of the material is not solid there, so the cooling is slower. So maybe this is some area of improvement for future changes in the model. So that's another example of the directional guidance that the software gives you. And if I take a look to the stress, I can do some experimentation as well here. So for example, I can display parts of the design that are not loaded much. So I'm going to threshold here and hide the pieces of the design that transfers values and keep the ones that are not loaded well. And if I will display it, you can see that actually these parts of the brake pads seems to be over-designed. I'm not sure why it is there. So if I will display the model, you can see that here's the part of the brake pad that is actually touching the rotor, and this is just a supporting area that's slightly bigger. But it looks like it could be smaller. So I can take the directional guidance and make this smaller. Well, another area that looks to be over-designed are these screws. Let's find out how big they are. If I will go to the inspect and select the diameter here, it's a 20 millimeters diameter. So I have two 20 millimeter screws that transfer the force. That's about 3,000 newtons on each brake pad. So it's a total 6,000 newtons. It's like 60 kilograms. So probably two 20 millimeters big screws are too big. So it looks like the common sense is aligned with the results of the simulation. So as a next step, I can take the directional guidance and make these smaller. Well, I'm not going to do it now because we are limited by time. This is just an example how the software is going to help you step by step to fine-tune your design and make it better and better. So the last piece is the cloud simulation. Cloud simulation is a new technology we are working on. It has multiple aspects, and today I will show you just little subset of it. So let's take a look to the first scenario here. We have the average part or small assembly, stuff like I was doing on today's class. We will focus only on one study at a time, and it's about just 100,000 elements in the mesh. So for local solve, I'm using my average computer with 8 gigabytes of memory and one 2.4 gigahertz CPU, so average computer. Even on this small computer, the solves take just seconds, in maximum minutes. So it's very fast and responsive. Our solver is optimized for linear static stress for these small parts and assemblies. If you will compare it with the cloud simulation, you have similar time experience. You don't see much improvements there because even the cloud solver is much more performant. The time is about the same. So you will see much better things in richer collaboration and data sharing. That's the value of the cloud simulation, even for the small assemblies. But I'm not going to talk about it today. I'm going to focus solely on the time aspect of it. So let's go to the second scenario. We have larger assembly with more complex parts, but still focusing only on one study at a time. So let's take a look how it works. So for local solve, I'm going to call the solve, and now it's happening. So it's going to mesh and solve, and because this is a big part, it actually takes time. So now I already spent 2 hours, 3 hours. I'm still waiting for my results, and in about 4 hours, I'm getting the results. So I spent 4 hours to do the analysis of this component. Now let's compare it with the cloud simulation. With cloud simulation, I click to the cloud solve, and it starts to do the job on the cloud. So I can continue to use my Fusion, I can review what's happening, I can go to the visualization, I can do whatever I want because my Fusion still works. It's not loaded by the heavy calculation task because it's happening on the cloud. And when the results are done on the cloud, I can see the notification here, and I can click to it and display the results. So it was just 1 hour here, and that's because the cloud worker is much more powerful. Here on my local computer, with just 8 gigabytes of memory, it started swapping to the drive, and that slows things a lot. So cloud work is much more powerful, and I'm saving actually 3 hours instead of solving 4 hours. I'm solving just 1 hour. And what's even more important, the Fusion is not impacted. So I'm saving actually 4 hours of my time because in my first example, the computer was slow and not responsive because it was fully loaded by the calculation. So nice saving even on that one scenario. And now let's take a look to the what-if scenarios. I have the same design, but I have 2 variants. And well, the reason to use the digital prototyping is to analyze the variance. That's the core of the value here. You want to analyze multiple variants, multiple what-ifs, to find out what would be the real solution of your problem. But let's take a look, even just 2 variants, how it looks with the local solve. I'm going to call the first one, and now Fusion is really busy. I see the modal dialog, I can't do much here, and my entire computer is slow because all the CPU power is used to do the simulation calculation. So I'm waiting the same 4 hours for the results of the first local solve. And when done, and when I see the results from the first one, I need to go to the second one, to the second variant, and do the same thing again. So I'm clicking to the solve again, and there are another 4 hours in front of me to wait for the results of that second variant. So that's pretty time-consuming thing just for 2 variants. Well, imagine if you have 6 or 4 variants, something more real, it would take a long time. So we invested 8 hours to wait for it. So you need to do sequential solves of 2 variants. Fusion is frozen and computer is not responsive because it's loaded by calculation. With the cloud simulation, it's very different. You call the cloud simulation for the first scenario, you see the indication it's solving, and you can immediately go to the second scenario and solve it again. And now you can do something else. You can maybe set up the third simulation or do whatever you want in your Fusion. And on the cloud, the calculation is happening without any impact to performance of your computer. So you can, for example, set up simulation of this knife during the solution of the first 2 variants. And then, as the results are calculated, you see again the notification, and you can view the results. So now you can analyze the results from the first simulation while the second one is still solving on the cloud. And in about 1 hour time, the results of the second simulation are coming as well because actually they run in parallel on the cloud. So you can see the results as well. So in the total time of 1 hour, you got both the results. And that's because there are parallel calculations. So independent of how much variance, how much what-ifs you are doing, it's still this 1 hour of the one solve. So here you are sequentially counting all together. Here there is no additional time because you have unlimited power of the cloud in your hands, and you can do parallel calculations there. Fusion is not impacted, so you are actually saving the full 8 hours your whole working day. That's the difference between, you know, sitting in the front of the frozen computer or being able to productively work. So that's just a quick preview of what's coming in the near future. We are going to deliver the cloud simulation that's going to make even the more complex calculation much easier to do. So let me summarize it, what we did today. We talk about the key concepts such as loads and constraints and so on. We verified the jack design and proved that it will work and transfer the load. We found a frequency that's going to break the wine glass. We fixed the problem with overheating using thermal, and thermal stress helped us to optimize the design of the brake system. And the cloud solve was kind of a technology preview of what's coming next. So before opening it to question, let me share credits with the team in Yechin who really helped to prepare the simulation for today's class. And now I'm here to answer your questions, so please feel free to ask. Okay.
Are there any tools to allow you to do a local mesh control? Do you see an area you would like to tighten up the mesh?
Not yet. We don't have this yet. We have adaptive meshing, so the software is automatically adjusting it, but we don't have a manual control there.
To expand on that, can you go back to the slide that showed where you were looking at the properties and the mesh size percentage?
Okay.
So there's something there I didn't quite recognize. Okay, so yeah, so if you adjust the minimum element size as a percent of average size, that would let it locally make the mesh smaller for high stress areas.
Right. And here, with the adaptive mesh refinement, you can actually let the software to identify the critical pieces, and in loops, it will make the mesh smaller and smaller on the areas that are critical. So you can switch this on, and it will now do multiple loops and kind of automatically optimize the mesh. And there is one nice thing that I actually didn't show today, and that's the voxel mesh we are using in a case there is an issue with the mesh. So with the traditional packages, what happens that if the mesh fails, you need to go back and simplify your model. You need to fix the model, actually change your model to help the software to generate the mesh. Here we took a different approach. If the mesh fails, we switch to the voxel-based meshing. That's kind of a different algorithm that does the mesh that maybe not perfectly covers the body, but it kind of bridges the areas with issues. So without asking a question, it gives you the solution. The cost is that the resolution is lower. However, engineers typically don't have the knowledge to do the simplification to fix the mesh issue. So the voxel mesh is kind of our plan B. When things go wrong, engineers still get their results. Yeah.
No, I was going to say the adaptive mesh refinement. Which is that on? Does it display a convergence?
Yeah, it does. So let's, well, let me go with a simpler sample here. And if I go with the adaptive mesh refinement, and I start the solve, you can actually see the convergence rate, and here there's a new icon, the plot, that actually shows you what happened during the solve. Does it make sense?
Yeah, it's very similar to what Inventor.
Right. It's based on the same solver.
Right,
Okay, any other questions? So I will be actually located today from 2 p.m. to 3:30 in the Fusion office here. So if anything comes to your mind, please come and we can talk about it. I can do some demos and we can show it. Okay, so thanks a lot for your time and see you next year.